Hi all, this is Bharatrar. I'm studying BTech first year, CSC A section, second semester. Today my talk topic is about characterization, modeling and analysis of organic light emitting diode with the different structures. Light emitting diode means LED. We'll discuss our introduction about this topic. Recent progress in organic light emitting diodes, that is OLEDs, have attracted considerable attention because they have wide viewing angle, fast response, and the potential of being mechanical, thin, and fixable. Since the report of first law voltage OLED using a simple bilayer structure, uh, intensive studies have been conducted for organic materials to device structures. Meanwhile, in 1989, phosphorates uh, organic light emitting diodes were demonstrated in which the emissive materials were osmosis complex dropped in poly, that is PVK. In same year, the use of platinum dropped in trace alumina, that is AlQ3, host as the phosphorescence light emitting was also reported. Since then, a platform has also been developed for the use of phosphorescent light emitting based metal complex in OLED technology. Phosphorescent emitted to coordinate device efficiency have been demonstrated by illustrating both singlet and triplet expectations through efficiency intersystem crossing enabled by the presence of heavy metal in the emitter. The efficiency of an organic electrolomicity device could be future improved by coasting the electron domain complex such as into the typical electron transporting layer. Meanwhile, other approach such as doping, doping and phosphorescent type imitators individually into two different hosts separated by an interlayer to form a fluorescence interlayer phosphorescence emissions to enhance the efficiency of OLEDs were developed. Now, currently there are a range of OLED structures for white light generation. The first white, the first white OLEDs was demonstrated by color mixing. One simple approach is to the co-deposit three phosphorescent emitters into a single host to form a single emission layer. Another approach is to use a fluorescent blue emitter together with a phosphorescent green and red emitter to construct a three color white device. The blue phosphorescent OLEDs generally has a short lifetime and large roll of issues as compared to their fluorescent counterparts. Nevertheless, blue phosphorus OLEDs are still attractive due to its high luminance efficiency and various approaches have been proposed to improve the efficiency and color quality. Mm. Tandem white OLEDs which compress vertical shaded layer electrically interconnected by a compound charge generation layer are reported in white OLEDs of a multiple emission layers such as separate emission layers. All through white OLEDs have already outperformed incandescent lights and halogen lamps in efficiency. Currently, their performance is still far for the target of general illumination in terms of high efficiency, long lifetime, light quantity, and low cost. Variation of temperature leads to non-uniform depreciation of its light output, which in which in turn increase the lu- luminance non-uniformity over time and efficient the lifetime of OLED. The optical measurement technical for determination of a spectral temperature distribution at organic layer level in OLED is proposed. By modeling electron theoretical interaction within OLEDs and preservers, describing local heat generation in all electrical active layer of OLEDs. Actually, prediction of OLEDs operationally characteristic can be obtained. OLED still lags behind the performance of white LED. Now we will discuss about characterization and PET modeling of OLED. Uh, two OLED devices from two manufacturers as shown in figure 1 are used in the study for device osmo organization, characterization and modeling. First, the OLED samples are luminate model number and Osram model number. These two OLED devices have two different structures. The structural difference will be evaluated progressively in the device characterization and modeling process. For both OLED samples, the organic layer have to be protected against air as they are sensitive to moisture and oxygen. A subtract is glued on the back of the each OLED in order to enhance the stability of the permeation barrels and terminal conditions. We will see figure 1. Once observe this figure 1A and figure 1B. This figure 1A and 1B shows the simplified device structure of for OLED. In figure 1, that is the x-axis is 97.6 meters. So same in figure 1A, the diagram shows like a square or rectangular. In figure 1B, it's look like a circle. The steady state measurements are obtained after 20 minutes of operations at representative electrical power levels at an ambient temperature of 200 degrees Celsius. The voltage change of this device during the process of heating and can be captured by using transit terminal testers based on the terminal transit measurement of the measurement procedure. The, the T3 test the T3 test capture the terminal transit response in real time, records the cooling or heating curve and then evaluates the cooling or heating curve in the order to obtain the terminal characterization. For voltage temperature sensitive calibration A 0.005, a current is applied in a temperature control oven at different ambient temperature of 25 degrees Celsius, 40 degrees Celsius, 55 degrees Celsius, and 70 degrees Celsius under pulsar current injection with a small duty circle by using Canadian 2400 source meter. Then the then the junction temperature is obtained in each case for the OLED through the use of voltage response curve and voltage temperature sensitively calibration using the T3 ester system. The nucleus and temperature description of the sample set different current levels are captured by Lumcam 1300 imaging photometer or colorimeter and LWIR camera. Once observe this figure, the important characteristics of OLED. The luminous intensity eye of a lighting device is an expression of the amount of light power emitting from light source within a solid angle which is a function of the junction temperature. In near room temperature, the emission intensity follows an exponential decay function that is I equal to I expansion minus Tj minus 25 degrees by Ti, where Ti is the characteristic temperature of the device and Tj is the junction temperature. These are important. And a high characteristic temperature implies that the influence flux is weakly dependent on junction temperature, which is describable feature and can be used as an indicator for comparing the OLED sample. The luminance intensity could be derived from the expression of luminance efficient E, which is given by E is equal to expression minus Tj by minus 25 degrees Celsius by T1. Uh, Next, we will see figure 3 and 3b shown the measures luminescent effects of the luminescent and Ostrom samples respectively. By fitting the measurements curve into the form of the characteristic temperature T1 of the luminescent and Ostrom samples are 1460 degrees Celsius and 512 degrees Celsius respectively. This suggests that the luminous effects of the luminescent sample decrease at a slower rate with increasing junction temperature than that of the Ostrom sample. Once observe these two graphs, uh, that the figure 3a represent junction temperature and figure 3b also different junction temperature. These are two different, that is one in figure 3a we are using 1416 and in figure 3b we are using 512. Uh, Figure 3 measures luminance efficiency, various junction temperature. The coefficient Ke defined in a PET theory is a measure of the drop characteristic of a luminance efficiency with the junction temperature and is a physical related to the characteristic temperature, that is Ke equal to minus 1 by T1. The coefficient Ke uh, can therefore be determined for the characteristic temperature of the device, where Ke for a luminescent OLED sample is about minus 0.0071 degrees Celsius and that for Orasram OLED sample is about minus 0.001 degrees Celsius minus. When the projected to 25 degrees Celsius, the luminescence effects EO of the luminescent and Osram sample are 25.8 and 14.8 representatively. Now, luminescent distribution and uniformity. Therefore, the luminance distribution and uniform of LEDs deserves more attention. The conductivity of the electrode material and the size of the pixel play an important role in the homogeneity. Assuming that p-type metal contact has equal potential and that the voltage across the vertical series resistance is much larger than Kt by E, the current distribution can be expressed as J of x equal to J of 0 expression minus x by d, where J of 0 is the current density, with the p type, x is the distance p type, uh, with this ds is defined as a current spreading length. ds equal to pe plus pt tp fn by pn, where pc is the specific p type contact resistance and pp and pn and tp by tn are electrical resistance and thickness of the pn p, type layer representatively. Uh, Here we say another formula Lx equal to Ej of x equal to Ej of 0 expansion minus x by ds. Here Ej is the efficiency coefficient relative the current density to lumens. Lumens uniformity can be defined as U equal to um, 1 minus L AV minus L minimum by L average, where L average is the average luminance, L minimum is the minimum luminance, so use the luminance uniform. If U is a closer to 1, the luminance distribution is a performance A. According to the measure result of the luminance distribution, different induction current level, the current spreading length DSN could be extracted based on a figure level. It is found that the variation ds with the induction current distributes a probability distribution. Therefore, it can be expressed as a ds, where ABC can be extracted by a curve fitting method. Curve fitting method based on the measure result in figure 12. In order to estimate the luminance uniformity, can be rewritten as Lx of it is found the various ds with the induction current distributes a parabolic distribution. Therefore, it can be expressed as ds equal to ai square plus bi plus c, where abc can be extracted by curve fitting method based on the measurement result in figure 12. The measurement, the electric power for OSRAM OLED is from 0.32 volts current and for 0.1 ampere to 2.2 2.22 volts current for 0.6 ampere. The position of OLED sample without heat sink is vertically while the absolute temperature of 20 degrees Celsius. It can be seen that luminance distribution are not uniform. In both cases, the luminance in the central region is the lowest. It should, however, he noted that such a non-uniform distribution is not caused by uneven thermal distribution. The measure surface temperature distribution across the two OLED samples at a curved current of 0.3 are displayed in figure 10. The thermal distribution has minor effects on luminance distribution. Once observed the stable, the maximum displacement in figure 10A and 10B are 1.1 degrees Celsius and 2.9 degrees Celsius respectively. It is noted the maximum temperature point do not appear in the center. The important observation indicates that the current spreading characteristic and the causes and homogeneity. We can observe figure 9 and figure 9b and level A and level B. In figure 9 shows that measured 3D luminance profile at current 0.3 ohms, 3 amperes. In figure level B, measure luminance distribution at different current A and B. Just observe that figure 12 shows that calculated current spreading length of luminance and oscillum OLED at different current. Red line shows luminance and black shows OSRM. Now the conclusion. It is demonstrated in the paper that OLEDs with different structures can be characteristic modeling and analysis with the combined use of the photoelectrothermal theory and spectral power distribution. Such approach covers the photometric, electric, terminal, and based on such a formula, the parameter of a OLED can be determined and compared with those of inorganic LEDs. With large surface area, OLEDs differ from inorganic LEDs in having such a lower thermal resistance and temperature sensitive. Their luminance flex curve are representatively more linear than those of inorganic LED, making it easy to implement timing control. All through OLEDs have generally higher heat dispersion coefficients than inorganic LEDs. Such a disadvantage is compensated by their large surface and contact areas, which act as a effective heat transfer paths. For OLEDs, the materials of the substrate could affect their thermal performance significantly. Substrate with a good thermal conductive were leading to a low thermal resistor. However, it is discovered that an uneven heat distribution over the surface of an OLED is not the main reason for non-uniform luminosity distribution. The main factor affecting the luminary inform is current distribution, which can be measured by current spreading length. A large the current spreading length is a better than luminance uniformity. Thank you.